This week we're going to cover the last two in our list of properties of the Laplace transform, and then we'll look at applying the Laplace transform to the solution of initial value problems. These last two properties of the Laplace transform have to do with getting some information about f of t from the Laplace transform f of s without necessarily inverting the transform f of s. In particular, they're called the initial value and the final value theorems. And the first of them, the initial value theorem, lets us find this right-hand derivative of f at t equals 0 without inverting the transform and finding little f of t, but instead just taking a certain limit involving the transform f of s. So if we have f of s and we're interested in this right-hand limit of f of t at t equals 0, we can get that limit without inverting the Laplace transform. So just to be clear, this is the limit as t approaches 0 from above of f of t, what we call the right-hand limit of f. This, in this particular case, is the limit of s times f of s as the real part of s goes to plus infinity. In general, when we talk about limits on the s-plane, we don't mean this. S can go to infinity in any direction, if you like, normally. But in this case, what we mean by this right-hand side of the equation is precisely this, the limit of s times f of s as the real part of s goes to infinity. So as we go off to infinity on the positive real line on the complex plane. And again, the theorem says that these are equal. So when might you like to use this theorem? Well, suppose that f is the output of a system, and we're feeding into that system an input such as a unit step. The unit step has a discontinuity at t equals 0. So in many cases, the output of the system into which you feed that unit step is also going to have a discontinuity at t equals 0. So if that output is f of little t, then f of 0 minus and f of 0 plus are going to be different. There's going to be a jump in the output at t equals 0. And if you're interested in finding out what that jump looks like without going to the trouble of inverting f of s, you can apply this theorem and find out the value of f of 0 plus. So again, the theorem claims that that right-hand limit of f of little t at t equals 0 is given by this limit on the right-hand side. Why is that? Well, there's a detailed proof given in the notes, a rigorous proof given in the notes, but we can sketch a kind of intuitive explanation of the result without going into all the detail of that proof. What's the idea? Well, we know by the derivative property of the Laplace transform that the Laplace transform of the derivative of f is equal to s f of s minus f of 0 minus. Okay. Now I'm talking about the derivative of f, but we're talking about discontinuities in f. That may seem a bit confusing, but before long we're going to introduce a kind of function called a generalized function that lets us talk about derivatives of functions that may have discontinuities like those that piecewise continuous functions have. So you don't really have to worry too much about the derivative, the existence of the derivative f prime, strange as it may seem. So just assuming that we can talk about a derivative of f even though it has some discontinuities. We know that our, and possibly a discontinuity right at t equals 0. Our derivative property tells us that the Laplace transform of f prime is equal to s times f of s minus f of 0 minus. So there's the s times f of s that appears in the initial value theorem, in the statement of the initial value theorem. So in other words, this is saying that s times f of s equals the Laplace transform of f prime of t minus f of 0 minus. And the Laplace transform of f prime of t will be the integral from 0 minus to infinity. We're talking about unilateral Laplace transforms here, as the statement of the theorem implies. So the integral from 0 minus to infinity of f prime of t e to the minus st dt minus f of 0 minus. Okay, so the theorem talks about taking the limit of this quantity, s times f of s, as the real part of s goes to infinity. So as the real part of s goes to infinity, what does e to the minus the real part of s times t look like? It's always a decaying exponential, so it's always 1 when t equals 0. But as the real part of s gets bigger and bigger, this exponential is going to decay faster and faster, right? The larger this real part of s is. It's a positive real part of s. So let's say as t gets bigger and bigger, this exponential convergence is going to happen faster and faster. So this is what happens as the real part of s goes to plus infinity. It's always equal to 1 at t equals 0, however. So what does that tell us about this integral? Well, let's just assume we can interchange the order of the taking the limit as the real part of s goes to infinity and performing this integration. And let's look at the integrand, f prime of t, e to the minus st dt. What's this? What's going to happen to this? What's this going to approach? Well, at t equals 0, we know that this is simply going to be f prime of t. In particular, let's look instead not at what happens to the whole integrand, but just at what happens to e to the minus st dt. So we know that at t equals 0, this e to the minus st dt is just going to be equal to dt. But elsewhere, if t is greater than 0, then as the real part of s goes to infinity, this exponential is going to decay faster and faster. So this is just going to go to 0. For t greater than 0. So intuitively, and again, there's a rigorous proof in the notes, the limit as s goes to infinity, in particular as the real part of s goes to plus infinity, is equal to, looking at our previous line, this integral from 0 minus to infinity of f prime of t e to the minus st dt, or rather the limit of that, minus f of 0 minus. Okay. But again, let's suppose that we can interchange the limit with the integration. Well, then we know that as s goes to infinity, this integrand is going to approach 0 for t greater than 0, and it's just going to approach f prime of t for t equal to 0. So we can say then that intuitively this limit is equal to, on the left-hand side, is equal to just the integral from 0 minus to 0 plus of f prime of t dt minus f of 0 minus. Because for t greater than 0, the e to the minus st approaches 0 as we let the real part of s go to infinity. So it's only what happens around t equals 0 that contributes to that integral. And what's this integral going to be? Well, the antiderivative of f prime is f, so this will just be f of 0 plus minus f of 0 minus. I seem to have made a sign error here. Yeah, up here, this should be plus. So the integral gives us f of 0 plus minus f of 0 minus. The f of 0 minuses cancel out, and this gives us f of 0 plus. That's the intuitive idea behind the proof of the initial value theorem. And again, there's a rigorous proof in the notes. Okay, so let's look at some examples just to illustrate its use. Suppose that f of s equals e to the minus s capital T times 1 over s squared. Now, by this time, you may already know what the inverse transform of this transform is, but suppose you didn't, and you wanted to know the initial value of little f of t. Well, according to the theorem, you can find that initial value by taking the limit as s goes to infinity of s times f of s, which is the limit as s goes to infinity, and again we mean as s goes to infinity along the positive real line, of e to the minus s capital T over s. Well, as the real part of s goes to infinity, this numerator is just going to go to 0, and the denominator is going to go to infinity. So this is going to give us 0. So according to the theorem, this should be that right-hand limit of little f of t, of f of little t. So let's just check to make sure that the theorem did in fact give us the right answer in this case. We can find, in this case, f of little t easily enough just by inverting our transform. So by now you may recognize 1 over s squared as the transform of a unit ramp. And multiplying that by this exponential in the Laplace domain corresponds to performing a shift in the time domain by the time shift property. So this is just a shifted unit ramp. In particular, it looks like t minus capital T times u minus 1, the unit step, t minus capital T. Right, the unit ramp is just little t times u minus 1 of little t. If we shift that to the right by capital T, we get t minus capital T times u sub minus 1 of t minus capital T. So again, this is just a shifted unit ramp. So as t approaches 0 from above, for this non-zero value, this positive value of capital T, this is going to, the limit as t goes to 0 from above is just going to be 0. So f of 0 plus equals 0. And that agrees with the theorem. We got that the limit of s times f of s was equal to 0. And similarly, f of 0 plus is equal to 0. So that agrees with the statement of the theorem. Here's another illustration. F of s equals 1 over s. So this is an even more recognizable transform. You probably recognize this as the Laplace transform of a unit step. So in this case, f of little t does in fact have a discontinuity at t equals 0. We know that. Let's just apply the theorem. The theorem says that if we take the limit as s goes to infinity along the positive real line of s times f of s, that will give us this initial value f of 0 plus. In this case, that is the limit as s goes to infinity of s times 1 over s, which is just going to be 1. And of course that is correct. If we check it, we know that in this case f of t is the unit step. So f of 0 plus, meaning the limit as t approaches 0 from above of f of t, is indeed equal to 1. So again, the theorem checks out. Let's look at another example. F of s equals s over s squared plus omega squared. What happens if we take the limit as s goes to 0 of s times f of s in this case? That's the limit, s goes to infinity, as s goes to infinity of s squared over s squared plus omega squared being just a positive real number, that's going to approach 1 as the real part of s goes to infinity. Okay, well, if you invert this transform, or as you can easily check, in this case, f of t is cos omega t, or if you like, cos omega t times the unit step. So, f of 0 plus, this initial value does in fact equal 1 in this case. Once again, the theorem checks out. So that's the initial value theorem. And again, if you know there's a jump in your function at t equals 0, this can let you compute it, or at least it lets you compute the right-hand limit without actually having to invert your transform. If you have your transform, you can get f of 0 plus without doing the inversion. And that theorem does come in handy sometimes. But our last property is called the final value theorem. So this has to do with computing a limit of f of t as t goes to infinity. And in practice, I think you'll find that this is a much more useful theorem. In particular, you'll make a lot of use of it in SE 380. So we'll go on to complete our list of Laplace transform properties by looking at the so-called final value theorem. But in order to do that, we first have to talk a little bit about so-called rational functions. So the topic of the next video will be rational functions. See you then.